Hello students, good morning to all. Welcome to your beautiful channel Firjan. Today's concept is electrostatic potential and capacitance, second lesson. It is the 8th video about electrostatic potential energy of an electric dipole when it is placed in external uniform electric field. When it is placed in its external uniform electric field, what is the electrostatic potential energy developed in the electric dipole when it is rotating in anti-clockwise direction? So that we want to derive an equation. Before that, we discuss what is uniform electric field, what is electric dipole, so that we discuss. Later we discuss electrostatic potential energy. Myself Reddy, it is your beautiful channel Firjan. See my videos, subscribe the channel and share to your friends and relatives. See, our actual concept is first we discuss electric dipole. So electric dipole now it has two charges. One is minus q, another one is plus q. So which are separated by very small distance 2a. It is separated by very small distance 2a. Means electric dipole is defined as two equal and opposite charges which are separated by very small distance. We call it as electric dipole. One is minus q, another one is plus q. See here, it is the center. From center, it is a distance. It is a distance. Means from center plus q, a distance, from center minus q, a distance. See here, its dipole momentum is in the direction of minus q2 plus q. So this dipole momentum we can represent p arrow mark. So that means it is the product of charge and length between them. So what is the length between them now here? 2a, charge is q. So what is the electric dipole moment? P equal to q into 2a. It is the product of charge and its length between them. It is a vector quantity. It is vector quantity. Its unit is, see here, charge na coulomb and length na meter. Coulomb meter is the unit of electric dipole moment. Electric dipole moment. What is the direction na? Minus q to plus q. Its dimensional formula is charge na ampere into time, meter na length. So that we can write m power 0, L power 1, T power 1, A power 1. It is the dimensional formula of electric dipole moment. So electric dipole means two equal and opposite charges which are separated by very small distance. We call it as electric dipole. Electric dipole moment, it is the product of charge and its length between them. It is vector quantity. Coulomb meter is the unit. Dimensional formula is m power 0, L power 1, T power 1, A power 1. So this is the basic information. Next, now uniform electric field. See, electric field lines are straight, parallel, equispaced. This we call it as uniform electric field. This is the uniform electric field. Means electric field lines are straight, parallel, equispaced. That electric field we call it as uniform electric field. Uniform electric field, every point, this point, this point, or this point, any point, electric field is same. That's why we can say it is uniform electric field. Here see, plus q we can place now. How it is now? Force is acting on plus q in the direction of electric field. So that is QE. For example, here we can place minus Q na, force is acting opposite to electric field. So that's why we can write minus QE. Minus means here opposite to electric field. So magnitude is same, opposite direction. Plus Q in the direction of electric field, minus Q opposite to electric field. It is the force. Force means charge into electric field. Charge into electric field. It is the basic information for uniform electric field. Now we discuss, see here, it is the uniform electric field. See, here electric dipole is placed. It is minus Q. it is plus q, plus q. See here in this one, here it is the center, it is the electric dipole moment. See, in the plus q, force is acting in the direction of electric field, so that is F1 equal to QE. On minus q is it is acting F2, that is minus QE. See, a minus means here opposite to electric field, that indicates. See here, before that, going to discuss electrostatic potential energy, we discuss about what is torque, moment of force, that we discuss. Later we can go to the actual concept. See here, first we discuss moment of force or torque. See here, it is the uniform electric field. Yeah, see, it is uniform electric field. Here it is the dielectric dipole. It is minus q, it is plus q. It is the direction of electric dipole moment. It is the p direction. See, its distance is from here to here, a. Here to here distance is a. Why not total distance is 2a between the minus q and plus q. See, it is the center. Here one force is acting, that is F1, we can write QE. Here one more force acting opposite to electric field, that is F2 equal to minus QE. This minus indicates opposite to electric field. What is the net force acting on the electric dipole now? I write here F net equal to F1 plus F2. So F1 is what? QE, F2 is minus QE. See here, what is the net force acting on the electric dipole? So F net equal to 0. F net equal to 0 means it is not in the translational motion. So that's why what happened now here. See, one more force is acting. One more force acting. See what is that now? Two equal and opposite forces which are not in the same line of action, then torque is acting on the electric dipole. It rotate about its axis. So that means here see, when two equal and opposite forces, when two equal and opposite forces act on dipole and not in the same line of action, and not in the same line of action, then it rotate about its axis of rotation, its axis of rotation. That force we call it as moment of force, that we can write tau. What is the name now? Tau. Tau means here torque or moment of force. To when two equal and opposite forces acting on dipole, acting on dipole and not in the same line of action. See, it is one direction, it is one, this is the axis of rotation, so not in same line of action. So that's why it rotate the body or the dipole in about its axis. It rotate the body about its axis, that we call it as moment of force. This we call torque. Due to torque, this electric dipole is rotating in the uniform electric field. Like this, it will be rotate. See here, here one torque is acting, here one torque acting. Because of this torque, it is moving down. Because of this torque, it is moving up. So like this, it will be about its axis. So this torque, we call it as here moment of force. Because of moment of force or torque, electric dipole is rotating about its axis, so that we call it as a rotational motion. In rotational motion, F net is 0, but moment of force is acting. So because of moment of force, so electric dipole is rotating about its axis in the external uniform electric field. So that torque now here, how to write now torque? So torque equal to force into perpendicular distance. Force into perpendicular distance. Force now here, it is the force. Perpendicular distance means from center of axis, axis of rotation, it is the perpendicular distance. How to find out this perpendicular distance now? See, it is the length A. Here making angle theta with electric, this is the electric field, it is the dipole moment. So angle between the electric field and dipole moment is theta. So A length, it has two components. One is A cos theta and A sin theta. A cos theta is horizontal component. A sin theta is the vertical component. It is the perpendicular distance. Here also see, here in this one we can draw the perpendicular. It is the angle theta. Here theta means here theta. So it is A cos theta. It is A sin theta. Here see, on plus q, torque is acting downwards, on minus q, torque is acting upwards. So both are in clockwise direction. It is also clockwise. It is also, here also torque acting, it is also clockwise direction. See, because of both are in clockwise direction, the object means here electric dipole is rotating about its axis. So that we call it as moment of force. Because of moment of force, it will be rotating in the external uniform electric field. Due to that, see here torque equal to what? Force into perpendicular distance. Here what is the net torque? Net torque equal to tau 1 plus tau 2. What is the tau 1 now here? So net torque equal to tau 1 means first net torque na this is tau 1, it is tau 2. See here what is the formula for torque? Force into perpendicular distance. What is the force here? QE, perpendicular distance is A sin theta. I write here QE A sin theta plus tau 2, this one force is here QE, perpendicular distance is A sin theta. See QE A sin theta. How many here? 2 QE sin theta, 2 QE sin theta, 2 QAE sin theta. Here we can write Q into 2A. We can write sin theta. Q into 2A means dipole moment. So dipole moment equal to Q into 2A. It is the electric dipole moment. So here we can write, instead of this we can write P, we can write what we get now here, PE sin theta. PE sin theta. What is the net torque now here? PE sin theta. When electric dipole is placed in the external uniform electric field, if force is acting, that force we call it as moment of force, which rotate the dipole about its axis. So that now what is the torque now? That moment of force now P is sin theta. See, P is this direction, means electric dipole moment is this direction. It is the electric field. See means how it will rotate. So clockwise direction means, see here, for example here, it will be by using screw rule. What is the direction of the torque we can find out? It will rotate in clockwise direction. How now? Screw will be inwards, so means direction of the resultant is inwards and P will be downwards. E will be, see here, P to E it will rotate. See, we can write here torque equal to P cross E. What is the torque formula na? P cross E. What is the torque acting on the electric dipole when it is placed in the external uniform electric field na? P cross E, or we can write PE sin theta. PE sin theta. This we can use here for finding or deriving electrostatic potential energy. This is the basic information for what is the torque acting on the electric dipole when it is placed in the external uniform electric field na? Torque is PE sin theta or P cross E. P cross E. See, now we discuss actual concept. What an actual concept? Electrostatic potential energy. Electrostatic potential energy of electric dipole when it is placed in the external uniform electric field. See, for that what we can do now here, see, in this one, first we can do here, it is the making an angle theta 1 with, it is the electric field, it is the electric dipole moment. See, it is the electric dipole moment, it is P. Yes na? See, angle between the electric field and electric dipole moment is theta 1. So we can rotate the electric dipole, it will be rotating this clockwise direction. We are rotating the electric dipole in anti-clockwise direction. It is plus q, it is minus q. What angle we can rotate now here? See, theta 2 angle we can rotate, theta 1 to theta 2. In this case we are doing some work against a moment of force. That work will be stored in the form of electrostatic potential energy. Electrostatic potential energy. For see here, for example, work done, we can write actually force into displacement, force into displacement in linear motion. So means in translational motion what we can write, work done equal to force into displacement. In rotational motion, instead of force we can write moment of force, that moment of force is torque into, instead of displacement we can write angular displacement, torque into angular displacement, we call it as work done in rotational motion. See, in translational motion na force into displacement, in rotational motion na torque into angular displacement. Torque is nothing but moment of force, this also force, it's also force, but it is in rotation, translational motion or linear motion. In this one we can say that in translational motion, torque is moment of force, it's also one type of force, but it rotates the object about its axis. In rotational motion, it is in translational motion, it is for translational motion, it is for translational motion, it is for rotational motion. Rotational motion, what is the work done na? So torque into angular displacement. See, for example here, theta 1 to theta 2 we are moving electric dipole against electric force or moment of force. So here that case, so how it will moving now, small angle, so means angular displacement d theta d theta d theta d theta, like this we can move, means here d theta is changing, means force is here, what type of force now here, variable force, work done by variable force formula is, work done by variable force formula is integral x1 to x2 f dx, we learn in this one in 11th standard. So work done by variable force in translation motion or linear motion formula is W equal to x1 to x2 f dot dx. See, for example, in rotational motion, how to write now? Integral theta 1 to, here it is displacement x1 to x2, here displacement is theta 1 to theta 2, that's why we can write here angular displacement, we can take theta 1 to theta 2. What is the force here? F here. But in rotational motion, what is the force now? Moment of force, torque into what na theta na here, d theta. So means tau d theta is the product of work in rotational motion. See, integral theta 1 to theta 2 tau dot d theta. So we can use that one. See here, what is the force now here? Electric force this direction. We are doing work in this against electric force. That's why we can take here work done by electric force. See, electric force this direction, here electric force over in this direction, so angular displacement is this direction. What is the angle between them now here? 180 degrees. Angle between force and angular displacement is angle is 180 degrees. See, we can take here work done by electric force, where to where, theta 1 to theta 2 tau dot d theta, we can write this one, we can remove dot product na, theta 1 to theta 2. See, tau d theta cos theta, we can write work done by electric force equal to integral theta 1 to theta 2 tau d theta cos 180. Cos 180, why we are taking na, electric force is this direction, angular displacement is this direction, both are in opposite. See, it is the force acting this direction, we are rotating this direction, angular displacement is from theta 1 to theta 2 this direction, anti-clockwise. So what is the angle between the force and angular displacement na? 180 degrees. Cos 180 na minus 1, we can write here integral theta 1 to theta 2 tau d theta minus 1. So we can write now outside here, see, work done by electric force equal to minus integral theta 1 to theta 2 tau means before only we can derive, so tau equal to what? Pe sin theta. What is P na here? Electric dipole moment. E is electric field, theta is the angle between the electric field and the electric dipole moment. See here, Pe sin theta d theta we can write here. See, Pe is the constant, so we can write outside minus Pe integral theta 1 to theta 2 sin theta d theta, we can write integral sin theta na, we can write, see here, work done by electric force equal to minus Pe Integral sin theta means minus cos theta where to where, theta 1 to theta 2 interval. See here, minus into minus plus Pe cos theta 2. First we can write upper interval, later we can write lower interval. So cos theta 1. See here, what is the work done by electric force? Now we are getting Pe cos theta 2 minus cos theta 1. Once again listen here. Say actually it is the electric dipole. It is due to electric force. It will rotating in this clockwise direction. We are applying external force and rotate the electric dipole anti-clockwise direction from theta 1 to theta 2 angle. So how much of work is done on electric dipole rotating against electric force? That work done will be stored in the form of electrostatic potential energy. So that we can derive now. So that case here actually work done. What now? Force into displacement in translational motion, in rotation, in linear motion. Force into displacement in rotational motion, instead of force we can write moment of force, that we call it as torque. And instead of displacement we can write angular displacement, tau dot d theta. It is in rotational motion. See, in this one here, see what is theta 1 to theta 2, not directly. First d theta angle rotating, next d theta, next d theta, like this d theta, theta small interval it will rotate. So we can take variable force, work done by variable force. In translational motion, work done by variable force formula is x1 to x2. x1 is displacement, x1 displacement to x2 displacement, f dot dx, that equal to integral theta 1 to theta 2 in rotational motion. When the object is in rotational motion, that case angle is theta 1 to theta 2, the angular displacement. So theta 1 to theta 2, instead of linear displacement we can use angular displacement, theta 1 to theta 2, tau dot d theta. It is the electric force, it is the displacement, both are in opposite. What is the angle now here? 180. T dot d theta means t d theta cos theta. Here we can write t d theta cos 180. Why? Because here both are in opposite. Displacement this direction, force is acting this direction. What is the angle between them now? 180. So we can write cos 180 minus 1. So minus we can write out, and see here minus we can write out. P is, so tau means here we know tau means moment of force. What is the formula? P is sin theta d theta. P we can write outside, integral theta 1 to theta 2 sin t theta sin theta d theta. Integral sin theta means minus cos theta, upper interval theta 2, lower interval theta 1. So first we can write upper interval, so minus into minus plus we can write. So upper interval first, later lower interval. So what we get now? Pe cos theta 2 minus cos theta 1. It is the work done by electric force. Actually what we want to do? Electrostatic potential energy, work done by external agent. What is the electrostatic potential energy formula now? Here delta U equal to actually negative of work done by electric force, or we can write positive of work done by external agent. External agent means external force. So we can know here delta U equal to U final. What is U final? Theta 2, U initial, theta 1. So means U theta 2 minus E theta 1 equal to what now? Work done by electric force is this one. Here what? Negative sign we can give now, that we call it a change in potential, that is potential energy. That is here minus Pe cos theta 2 minus cos theta 1. See here we get U theta 2 minus U theta 1 equal to minus Pe cos theta 2 minus cos theta 1. It is the electrostatic potential energy. If here let theta 1 equal to 90 degrees, U 90 equal to 0. So this we can assume this. This is our assumption. See what we can write now, instead of theta 1 we can write 90, U 90 equal to 0. Why now? Here see U theta 2 minus U 90, that equal to minus Pe cos theta 2 minus cos 90 we can write. So cos 90 value 0. See here U 90 also 0. What we get now? U theta 2 equal to minus Pe cos theta 2. Here see theta 2 is there, here we can write theta 2. U theta we can write now here minus Pe cos theta we can write. It is the electrostatic potential energy when it is placed in the external uniform electric field, that is u theta equal to minus Pe cos theta. It's we can write u theta equal to minus P dot E, dot product of electric dipole moment and electric field. We can write either this one or this one, we can write both are connected. What is the electrostatic potential energy when it is placed in the external uniform electric field na? So what is electrostatic potential energy equal to u theta equal to minus Pe cos theta, or we can write minus P dot E. It is the formula for electrostatic potential energy. It is the formula for torque acting on the electric dipole. See here, from here we know here delta U equal to minus of work done by electric force or positive of work done by external. This is the definition of electrostatic potential energy. So from the delta U equal to u theta 2 minus u theta 1. It is the final, it is the initial. U theta 2 minus u theta 1, that is minus Pe cos theta 2 minus cos theta 1. So we can write here u theta 2 minus u theta 1, that equal to minus Pe cos theta 2 minus cos theta 1. Here theta 1 equal to 90 we consider, and u 90 equal to 0. So we can substitute here, we can get u theta 2 equal to minus Pe cos theta 2 minus cos 90. Cos 90 is 0. We can get here u theta 2 equal to minus Pe cos theta 2. Here theta 2 is there, here theta 2, here theta means here we can write theta, that is u theta equal to minus Pe cos theta. So that we can write u theta equal to Pe cos theta means AB cos theta, A dot B means AB cos theta. Like that Pe cos theta means P dot E. P means electric dipole moment, E means electric field. It is the derivation of electrostatic potential energy of an electric dipole placed in uniform electric field. Placed in uniform electric field. What is the formula? U theta equal to minus Pe cos theta, or we can write minus of P dot E. Torque na tau equal to Pe sin theta. It is, these two are the formulas we can use when an electric dipole is placed in the external uniform electric field. It is for electrostatic potential energy. It is for moment of force or torque acting on the electric dipole when it is placed in the uniform external uniform electric field. So now we can do some problems according to this. See once. First, na, we have some special cases is there when electric dipole is placed in external uniform electric field. What are the special cases na? So we can discuss that one. Three special cases is there. See first one. See here, for example, here this is the uniform electric field. Yeah, it is uniform electric field. Here electric dipole is there. This is plus q, it is minus q. Here it is force is acting in this direction F1, that is QE. One more force acting in this direction, that is F2, that is minus QE. Yes, now why? Because opposite to electric field. Here it is the electric field. Here it is the direction of dipole moment. So angle between electric field and dipole moment is theta. This case some terms we can use, that is what is the electric dipole moment, P equal to Q into 2a, and what is the torque acting on this one, Pe sin theta. So that we can write torque equal to P cross E, we can write. So what is the electric potential energy na? U theta equal to Pe cos theta, we can write minus Pe cos theta. So that we can write u theta equal to minus P dot E, we can write. So one more here, what is the net force acting on this one now? Always zero. This is always zero. It is the electrostatic potential energy. It is the torque acting on the electric dipole. So it is the electric dipole moment. These are the terms we can use when the electric dipole is placed in the external uniform electric field. By using this, we can write three special cases is there. First one now here, theta equal to 0. Theta equal to 0 means here electric dipole and electric field both are in same direction. For example, see here, it is the electric field, direction of electric field, it is the direction of electric field. Here we can place the electric dipole. So it is plus q, it is minus q, it is minus q, it is plus q. See here, force is acting in this direction, F1. So one more force is acting in this direction, F2. See here it is F1 equal to QE, here F2 equal to QE, both are in same magnitude, opposite direction. See here, it is the axis of rotation. See, this is the F1, it is the F2. Two equal and opposite forces act on same line of action. Same line of action na torque is 0. Not in same line of action, not torque, not 0. Here first one, so F1 equal to QE, F2 equal to minus QE. What we can write now here, F net. F net equal to minus QE plus QE. So means what is the F net value? 0. So means F net is always 0 when electric dipole is in external electric field and it is rotating about its axis now, means that means in rotational motion, that case F net is 0, always 0, always 0. See here, it is the force, it is also force, both are acting in opposite direction, but it will be in the same line of action, that case torque equal to 0. How it is now? Torque formula is Pe sin theta. See here, Pe sin theta. What is the angle here? Theta equal to 0. Why? Because it is the electric dipole moment. It is the electric field. Both are in same direction. Theta equal to 0. So here we can write 0 now. Pe sin 0. What we get? Torque equal to 0. So means torque 0 and net force also 0. So then we can say that it is in equilibrium. Equilibrium, it is in equilibrium means torque and net force both are acting on electric dipole is 0. That case we can say that, so electric dipole is in equilibrium. Why torque 0 na? Two equal and opposite forces which are acting on the electric dipole, which are in the same line of action. See, it is the line of action of electric dipole and force also acting in the same. So that's why torque is 0. So in this case, net force and torque both 0 means electric dipole is in equilibrium. What type of equilibrium? Now we have here three equilibriums is there actually: stable equilibrium, unstable equilibrium, neutral equilibrium. We have stable and unstable. See in this case, see here, it is F net equal to 0 means it is in translational equilibrium. Translational equilibrium. Torque equal to 0 means we can say it is rotational equilibrium. Rotational equilibrium. See, both we can say that mechanical equilibrium. Both we can say that mechanical means F net equal to 0 translational, torque equal to, net torque equal to 0 rotational. Both we call it as mechanical equilibrium. This case, what now here see, it is the electric dipole. It will be moving upward, slightly displaced, and release it now. What happen? It will get again its original position. So means why now here? So means after displacing slightly, it will get original position. So that equilibrium we call it as stable equilibrium. What is the potential energy in this case now? U theta equal to minus Pe cos theta. See here, U theta equal to minus Pe. What is the theta value here? 0. So we can write cos 0. Cos 0 is 1. So what we get now? Minus Pe. Means minimum potential energy we get. Minimum potential energy means electric dipole has minimum potential energy. When minimum potential energy, electric dipole has minimum potential energy, that we can say that here stable equilibrium. What type of equilibrium now? This one, stable equilibrium. Stable equilibrium means if the electric dipole is slightly displaced, it's after displacing means and release it, it will get its original position. So that we can say that stable equilibrium means after slightly displacing the electric dipole and release it, it will get its original position. That equilibrium we can say that stable equilibrium. In stable equilibrium, what is the potential energy now? Minimum potential energy. Why we are it is getting stable equilibrium now? Electric field always tries to keep the dipole in the direction of its own direction. So due to that, electric dipole tightly displaced, after release it, it will get its original position. So means stable equilibrium means if an object is slightly displaced, after release it, it will get its original position, that we can say that stable equilibrium. Here electric dipole slightly displaced from the equilibrium position, again it release it, what happened, it will get its own position because of electric field always try to align the electric dipole in the direction in its own direction only. So that's why it will be gets its original position. See here, stable equilibrium means stable equilibrium means, see here, means after slightly displacement, or we can write if an an electric dipole electric dipole slightly displace slightly displace displace and release, it gets its original position or equilibrium position. This we can say that stable equilibrium. In this case, electric dipole has minimum potential energy. Why? Because u theta equal to minus pe cos theta. Theta is 0, cos 0 means 1, so minus pe, minimum potential energy. See here, why it will be getting equilibrium position na? Electric field always always try to keep the electric dipole electric dipole electric dipole in its own direction, in its own direction. Because of this, after slightly displacing electric dipole, it gets its original means equilibrium position. So this is the first case. What is the first case now? Theta equal to 0. Theta equal to 0 means it is the direction of electric dipole moment, it is the electric field, both are in parallel, means theta equal to 0. This case, so F net equal to 0. F net is always 0 when the electric dipole is placed in the external uniform electric field. So torque equal to 0. Why? Because two equal and opposite forces which are in the same line of action. So because of that, torque equal to 0. On the same way, we can use formula by find out what now torque equal to P is sin theta, P is sin 0 na, what we get torque equal to 0. Means net equal to 0 means translational equilibrium, torque equal to 0 means rotational equilibrium. Both we call it as mechanical equilibrium. When the electric dipole is in equilibrium, so if it slightly displaced from its original position, after releasing, it gets its original position again. So that means here it has potential energy is minimum, that we can say that stable equilibrium. So in why it will be get stable equilibrium na? Electric field always tries to keep the dipole in its own direction. Because of this reason, it will get its original position. So means that equilibrium we call it as stable equilibrium. See here, theta equal to 90 degrees means case 2. Case 2 what now? Here electric dipole is placed perpendicular to electric field. It is the electric field, it is the electric dipole, it is minus q, it is plus q. See, this is the direction of electric dipole moment. What is the angle now? Here 90 degrees. Here F net equal to 0, it is always 0. What is the torque now? Here torque equal to Pe sin theta formula. So sin theta means here Pe sin 90, sin 90 value 1. So we can get torque equal to Pe, means we can get torque is maximum torque when the dipole is placed perpendicular to the electric field. What is the potential energy now? Here Pe minus Pe cos theta. So theta is 90, so means minus Pe cos 90. 90 means 0. So what is the potential energy now? Here 0. When the electric dipole is placed perpendicular to the electric field, what is the torque na? Maximum torque. What is the potential energy na? 0. So it is electric dipole, it is the electric field. So what is the angle between the dipole moment and electric field na? 90 degrees. This case F net equal to 0, torque is maximum, potential energy is 0. Next third case, last case. See here, what is the last case now? Here see, theta equal to case 3. Case 3 means here see, it is the electric field. Yeah, see, it is the electric dipole. Here minus q is there, here plus q is there. So means it is placed theta equal to 180 degrees. So electric dipole moment is left side and electric field is right side. This case, what is the angle between the electric dipole moment and electric field na? Theta equal to 180 degrees. Both are in anti-clockwise direction. Anti-clockwise direction. What is that case na? Net force acting on this one na? Net equal to 0 and torque na here see Pe sin theta. What is Pe sin 180 na? Angle is 180. What is sin 180? 0. Torque equal to 0. Again net force and torque is 0. This we can say that equilibrium position. Equilibrium position. In this case, what type of equilibrium na? This one, see here, this plus q will be slightly displaced. What happened now? It will not gets its original position. It will rotate and align it in the direction of electric field. Electric dipole will be aligned in the direction of electric field. So means here not getting its original position. So that we can say that unstable equilibrium. If an electric dipole is slightly displaced after releasing it, it's not gets its original position. That equilibrium we can say that unstable equilibrium. Why it will be gets unstable equilibrium na? Electric field always tries to keep the electric dipole in the direction of electric field. Because of that, if slightly displaced, it's not get its original position. So that we can say that unstable equilibrium. Unstable equilibrium. Equilibrium. In this case, what is the potential energy now? Here see minus Pe cos 180. So cos 180 na minus 1. Already minus Pe minus 1 na minus minus plus Pe we get. So means it is maximum potential energy. When the electric dipole is placed anti anti-clockwise to the means or anti-parallel to the electric field, that case what is the angle now? 180 degrees. That case what is the net force now? 0. Torque is 0. Net torque 0. So we can say that equilibrium. What type of equilibrium now? That is unstable equilibrium. That case what is the potential energy now? Maximum potential energy is acting on the electric dipole. Electric dipole. These are the three cases. First case is theta equal to 0, stable equilibrium. Second case, in stable equilibrium, F net 0, tau net 0. What is the potential energy? Minimum potential energy. In second case, theta equal to 90 case, F net equal to 0, torque is maximum, potential energy is 0. So third case, theta equal to 180 case. In this case, electric dipole is placed against the electric field. So means that case what is the angle between them now? Here 180 degrees. That case F net equal to 0, net torque equal to 0. We can say equilibrium. What type of equilibrium now? Unstable equilibrium. Unstable equilibrium means if an electric dipole is slightly displaced from its original position, after releasing it, it's not gets original position. So that we can say that unstable equilibrium. That case what is the potential energy now? Maximum potential energy is having the electric dipole. So these are the three cases, special cases for electrostatic potential energy of an electric dipole placed in uniform electric field. Yes na? See, next we discuss some problems according to this. So what is na first problem na? Here see, it is the electric field, uniform electric field. We know uniform means straight, parallel and equispace. Here we can place one electric dipole. It is plus q, it is minus q, it is a direction of electric dipole. It is the electric field, it is dipole moment. What is the angle now? Here theta. See here, in this case, here force is acting F1, here force is acting F2. See, in this case, what we can do now? Find work done by external agent in rotating electric dipole. Rotating electric dipole from theta equal to 0 to theta equal to 180 degrees. Means electric dipole is rotating from theta equal to 0 angle to 180 degrees. That case, what is the work done by external agent? That we want to find out. For that, what we can do now? Work done by external agent is stored in the form of electrostatic potential energy. What is the formula for electrostatic potential energy? U theta 2 equal to minus Pe cos theta 2 minus cos theta 1. Cos theta 2 minus cos theta 1. Theta 1 is what here? 0. Theta 2 is what here? 180 degrees. We can write here U theta 2 equal to minus Pe cos 180 minus cos 0 we can write. See here U theta 2 equal to means U theta equal to we can write minus Pe cos 180 means minus 1 cos 0 1. So already minus is there, minus 1 minus 1. So minus 2 minus Pe minus 2, now minus into minus plus 2e. What is the potential energy stored in the electric dipole when it is placed in the external uniform electric field and rotating from theta 1 equal to 0 to theta 2 equal to 180 degrees na? So we can write here delta u, we can write better change in potential. Yes na? See change in potential formula is minus Pe cos theta 2 minus cos theta 1 minus Pe cos theta 2 is 180 cos theta 1 is 0. We can write here minus 1, it is minus 1. So minus into minus plus we can get, so 2 Pe. What is the potential energy stored in the electric dipole when it is rotating from theta 1 equal to 0, theta 1 0 degrees to 180 degrees now? It is the potential energy stored in the electric dipole. See next one, second problem now here. See second one, see it is the electric field, uniform electric field. Here see electric dipole is placed, this is the initial condition, it is minus q, it is plus q, it sees here 60 degrees with the electric field. See here it is the dipole moment. See one more, it will rotate from 60 to this direction means plus q and minus q. Here angle is 60 degrees. Find work done by external agent from final to initial position, final to initial position. So that we want to find out what is the work done. So for that what we can do now, here theta 1 equal to 60 degrees, theta 2 means here to here, here to here total is 180. This we can remove now, 180 minus 60 we can get the theta 2 value. What is the theta 2 value now? Here 180 minus 60 means theta 1 equal to 60 degrees, theta 2 equal to 180 minus 60 degrees, we get the theta 1 value. What is that one? 120 degrees. See here work done by external agent we can write, it will be stored in the form of electrostatic potential energy, that is delta u equal to minus of Pe cos theta 2 minus cos theta 1. Here theta 1 is 60, theta 2 is 120. We can just substitute here delta u equal to minus Pe cos theta 2 means 120 and cos theta 1 minus cos 60 we can write. So cos 120 means minus Pe, here minus 1 by 2, here cos 60 is 1 by 2, minus 1 by 2 minus 1 by 2 na, 2 by 2 means minus 1, we can get minus into minus plus. What is the potential energy stored in the form in electric dipole when it is rotating from theta 1 to theta 2 degrees means 60 to 120 degrees na? So Pe potential energy, what is na potential energy? Pe. It is the second problem. See last problem, it is important. See find the angular velocity of the electric dipole when it is released from the rest and it crosses the equilibrium position. See last problem, see here it is the electric field. Here electric dipole is placed, this is the electric dipole, so means here plus q, it is minus q. What is the angle between the electric field and electric dipole moment now? Here 90 degrees. This case find the angular velocity, angular velocity of dipole, dipole when it crosses or passes the mean position. While passing mean position, what is the angular velocity that we want to find out? When it is the position when it will rotating to here, this question, what is the, in this case, what is the angular velocity, that we want to find out. Means here, see, it is in rest, so release from rest, release from rest. Now what happened here, it has potential energy, maximum potential energy, kinetic energy 0. It will reaches to mean position. Now it will get potential energy and kinetic energy, so both. So means what happened here, potential energy is converted into kinetic and potential energy is there. So we can use here conservation of energy, conservation of energy we can use. So in this case, see here, what na, initial mechanical energy which is equal to final mechanical energy. What is initial mechanical energy na? So initial potential energy plus initial kinetic energy, that equal to final potential energy plus final kinetic energy. We can write, what is the formula for potential energy na, minus pe cos theta. So kinetic energy formula na, half I omega square. It is the formula for kinetic energy. What is the formula for kinetic energy? When the object is in rotational motion na, half I omega square. Here I means moment of inertia, moment of inertia, and omega is angular velocity, means rate of change of angular displacement, we call it as angular velocity. Moment of inertia means it is the product of mass of body into perpendicular distance from its axis of rotation, perpendicular distance from its axis of rotation, axis of rotation. It is the formula for moment of inertia. Moment of inertia, how to write na, I equal to mass of body m in perpendicular distance, square of perpendicular distance, sorry. What is the moment of inertia na, mass of body into square of perpendicular distance from its axis of rotation, means m a square. For example, here electric dipole, it has plus q and minus q. It is the center, means axis of rotation. From here to here distance is a, here to here distance is a. See, what is the moment of inertia for electric dipole na? See here, it has mass m. What is the perpendicular distance a? So means m a square, mass into square of perpendicular distance from its axis of rotation. Here it has mass m. What is the perpendicular distance na? Here a means m a square. See here, 2 points is there, minus q and plus q. So we can take here m a square, m a square. 3 points is there, one more. So means like that, means here moment of inertia equal to m a square plus m a square. What is the moment of inertia for electric dipole na? 2 m a square. So we can use that formula here. What is the moment of inertia of electric dipole na? 2 m a square. This we can use here. See here, initial mechanical energy which is equal to final mechanical energy, potential energy na, minus pe cos theta. So means here half I omega square. So initial kinetic energy is 0. So why? Because it is at rest. See, final potential energy pe cos theta plus potential and kinetic energy na, half I omega square. So what is the first case, theta equal to 90? I write here minus pe cos 90, cos 90 na 0, already 0 here. So minus pe cos na, it will reach us to equilibrium position, theta equal to 0 cos 0, 1 half I means what here, 2m a square omega square, like this, 2 cancel. What we can write now here, see. So here 0, this side what we get, minus PE. Why? Because cos 0 equal to 1. So minus PE plus m a square omega square we get. So PE changes to this side. So plus PE, that equal to m a square omega square. P means electric dipole moment. What is the electric dipole moment? Q into 2a. We can write here Q into 2a into E, that equal to m a square omega square. This a cancel. What we get now here, 2QE equal to MA omega square. So it will changes to this side, it will changes to here, MA omega square equal to 2QE omega square equal to 2QE by MA, omega equal to root of 2QE by MA. It is the angular velocity of the electric dipole when it is released from vertical position to equilibrium position. Yes, na? So this one, see, conservation of energy we can use mechanical energy, initial mechanical energy, final mechanical. Initial mechanical energy means initial potential, initial kinetic, initial final potential, final kinetic. So kinetic energy formula is half I omega square. I means moment of inertia. Moment of inertia for electric dipole is 2 ma square. We derive already. See that we can use here. It is Pe cos theta cos 90 0. I omega square means kinetic energy initially is 0. Why? Because at rest only. It released from the rest only. See, final potential energy minus Pe cos theta. Theta is 0. Why? Because it reaches to crosses the equilibrium position. So that case theta equal to 0. Half I means 2 ma square omega square. 2 cancel, cos 0 1. So minus Pe plus ma square omega square. So Pe changes to that side, we can get ma square omega square. P means electric dipole moment, P equal to q dot 2a. We can write here q dot 2a equal to ma square omega square, a cancel. What we get now? 2QE ma omega square. Ma omega square equal to 2QE. Why? Because it will changes to here, it is changes to here. Omega square equal to 2QE by ma. Omega equal to root of 2QE by ma. Means what is the angular velocity of the electric dipole when it is released from 90 degrees to 0 degrees reaches na, that case what is the angular velocity? 2QE by ma. Here q means charge of the charge and E means electric field, m means mass of the charge, a means here distance between axis of rotation to charged particle. Yes, na? So this is the omega angular velocity of the electric dipole when it moves from vertical position to horizontal position, crosses horizontal position. That means theta equal to 0 means mean position. So this is the problem. So this is the information about electrostatic potential energy of an electric dipole when it is placed in the external uniform electric field. We discussed torque, what is Pe sin theta, what is potential energy minus Pe cos theta. So on the electric dipole moment, P equal to Q into 2a. Yes, na? So what is the angular velocity when it is moving from vertical to horizontal? So that is root of 2QE by ma. Yes, na? This is very good information. Please see my videos and subscribe my channel and share to your friends and relatives. Thank you.